All right, so last day we did that quick experiment on Le Chatelier's principle, and using the colors, again, it was very qualitative. You hopefully got an opportunity to see those equilibrium actually shift due to the color change, which is excellent. We're going now back to some mathematics here, and we're going to be taking all of those different types of problems that we learned how to do with just a general equilibrium, and we're going to apply them to solubility, to the dissolving of a substance. Now this kind of, I guess, the next two sections kind of mimics, replays what we did in the grade 11 when we talked about the solutions unit in grade 11. We talked about solubility, and we then learned about how to calculate concentration and things like that. We're not going to do that, but we're going to talk about solubility here, so that kind of is a link there. But this time it's going to be very quantitative. We're going to talk very mathematically about solubility and whether something precipitates or not, mathematically. And then in grade 11 we also talked about acids and bases after that, and also in the next I guess chapter where we're going to have a new test, we'll also be talking about acids and bases. But now we're doing this on a much higher level, where we can actually now apply our concepts of equilibrium to these two concepts of solubility, all right, and acids and bases. Don't write down this next slide. This is just a information type thing. So last year when we talked about solubility, we talked about it in two locations. We talked about it when we introduced double displacement reactions, and in order to determine whether the double displacement reaction was successful or not, it needed to produce a solid, right? So I guided you to the table where you would find the two ions, and if it was a solid, it had an S, or if it stayed aqueous, it was AQ, right? Remember that good stuff? And that's essentially how you determined whether something was going to form a precipitate or not, okay? And this week we will also talk about forming precipitates, but right now I just want to talk about solubility. They're very related to each other. So again, just like last year, a little discussion on solubility, but this is review, no need to write it. It's a measure of the amount of substance that can dissolve in a given volume of solvent at a particular temperature to create a saturated solution. So that goes back to all of that good stuff. A saturated solution no more can dissolve. It's dissolved as much as it can. A given volume of solvent, because we have to keep that volume constant so we can compare different solubilities, and a given temperature, and that dealt more again with the solubility curves. All right, remember we had those solubility curves, and we kind of read how much could dissolve at a particular temperature. We're gonna take this and apply it all now to an equilibrium situation. We had terminology like highly soluble or slightly soluble and insoluble. We can use those terms again qualitatively to describe a substance. But now we want to talk again mathematically on how we describe solubility and how much it can dissolve. No need to write this stuff down. Again, these are just examples of these different amounts of solubility. Sodium chloride is highly soluble. Notice we're using the equilibrium arrows, and that reflects the fact that solubility is an equilibrium situation. And again, what that means is in a beaker that has water, that has a solid sitting at the bottom, and it's got a saturated solution above it, we have continuous dissolving and continuous solidification going on as that system sits there. So again, it's an equilibrium situation. Highly soluble. In terms of our equilibrium, highly soluble means we have lots of ions in solution. And in terms of equilibrium constants, it means it sits to the right. So if something is highly soluble, it will have a very large K, which means a lot of ions are able to exist in solution. Soluble, slightly soluble, will have those Ks that are kind of in the middle. And if it's very low solubility, we essentially say insoluble. It means the K is very small and very few ions are produced, and most of it sits there as a solid. All right? So we're now going to apply this idea of solubility to our equilibrium systems. So you can write this down, a solubility equilibrium. And maybe just for a visual representation, because I have drawn this before, but, oh, why have we gone back to green? It was nice and yellow before. That's odd. But in a solubility equilibrium, right, we've got that solid, and I'll just put here, I'll just use NaCl, NaCl solid, right, down there in the bottom. And what we have going on for that equilibrium here, I've got the Na plus Cl minus. And so continual kind of dissolving, all right? And then the opposite arrow, continuous deposition, solidification, whatever term we're supposed to use when it comes to, something crystallizing out of a solution. But it's continuously dissolving and continuously depositing at the same rate. It's a classic equilibrium. So even though you might think that that saturated solution is just sitting there quietly doing nothing, it's dissolved as much as it can, in an equilibrium situation, we know that it's continually, producing product, which in this case are the ions, and continually producing reactant, which in this case is the solid, all right? So that's what we mean by a solubility equilibrium. And if it's in the equilibrium, it means we have a constant that goes with it. And in this case, we call it the solubility product constant. You'll notice it's not called the equilibrium constant, but it essentially is. Again, the solubility product constant was probably mathematically or experimentally discovered before the idea of equilibrium. And once the concept of equilibrium was established, chemists realized that we were really looking at an equilibrium situation and therefore giving it the constant K. And the subscript SP to stand for solubility product. And I'll explain why they call it a product. And what they mean there is literally a mathematical product, a multiplication. They're not talking necessarily about the ions as the products of a reaction. They're talking about mathematically a product. We're not going to be looking at solubility curves in this course, but we know that solubility is affected by temperature. We also know that an equilibrium constant is affected by temperature. And so now, hopefully, maybe in our minds, we can see the link between this temperature dependency in dissolving and the fact that it's an equilibrium situation. And now the reason there's a temperature dependence in solubility is because there's a temperature dependent, or dependency, I guess, in the constant K. That's the same temperature dependence we're talking about here. Yeah, the purple thing was a link to that particular page. I don't have that, but on page 725 in the back of your book. So if you're doing some questions that out of the textbook that need a solubility product constant, that's where you're going to flip to get that data. On this sheet, I believe every time you need a KSP, I supply it for you. I give it to you in the question. And on a test as well, I simply supply it for you in the question. So if it's needed at the very end in brackets, I'll just say the KSP is. Now the little bullet here in yellow here, usually the higher the KSP, the more soluble the substance is. And that makes good sense. In a solubility chemical equation, even though it's a physical change, we have our ions on the right, we have our solid on the left, and if the K is large, then it means there's lots of ions, right? It means that the product is large. It means there's a lot of dissolved stuff. So the higher the KSP, the more soluble it is. Notice I say usually, and that's because there's a little dependency on how many ions there are in the solution. And we'll see that dependency here in a moment. Don't write these down. These are just some examples of some KSPs. We'll come back and look at them in a moment. But if you check in the back of your book, I don't know if these came from the back of that book, they came from somewhere else, or even in the big, the big Bible of chemistry, you can find all this information. You can see here we've got a barium carbonate. It's got a KSP of 2.6 times 10 to the minus 9. Again, keep in mind you're looking at the power of 10 to get an idea on the size. So that's fairly small, which means this stuff isn't dissolving very, greatly. But then we've also got the iron 2 hydroxide, and you can see there it's 4.9 times 10 to the minus 17. Now you might think, whoa, the solubility of the iron 2 hydroxide is significantly less than that of the barium carbonate. And we're going to find out by the end of the class that it's not as less as you might think, and that has to do with the mathematics involved in the calculations, which we will do in a moment. All right? Okay, so at this point, we're going to come up with some equations for the solubility of various types of salts. Excuse me. Now, you will not find the derivation of these equations in your textbook. You will find them in this textbook, my first year university book. Well, it's not mine. This is Mr. Mueller's. Mine's at home. Looks just like it. Some high school teachers feel, no, make them go through all of the ice tables. Make them do it all from scratch, right? Good practice. We've done quite a bit of practice with ice tables. I'm a firm believer of, if you can derive an equation, then why not derive a general equation and use the equation? And so I'm a fan of coming up with a derivation, getting an equation that you've now completed, and then using that equation to its fullest extent. That's why we derive equations, right? That's why we put equations together in physics to make a simpler one so that we can gain some understanding about it without having to go through all the steps. So I'm a fan of coming up with the general equations and having you memorize them and use them. Now, I don't like this color green, but that's what we're stuck with here today. Unless I can turn it into yellow. Can I turn it into yellow? Setting? No, forget about it. Okay. Now, be aware, this is the type of equation that I can make you derive on the test as well. All right? So if I want you to derive it, I might say something, could you please, in this question, derive the equation for the solubility of a salt of type MX? You'll do the derivation, and then I might say, use that equation to answer this question. So be aware, the derivations are also fair game, right? That's part of deriving an equation. You've got to be able to do that as well. So what do I mean by a salt of MX? Well, that's black. That's absolutely no good. E.g., an example of a salt of MX is something like NaCl. In other words, it's made up of one metal and one nonmetal, with M being metal. Everybody kind of understand that? Now, it doesn't have to be of oxidation state 1 and 1. It could be something like calcium oxide or magnesium oxide, right? So it could be something like MgO as well, as long as it's to the ratio of 1 to 1 for the ions. Are we okay with that concept? Now, in order to derive the solubility, I do need an ice table. So I'm going to put in the general equation, Mx solid, and I apologize for the green. I don't know why it defaulted back. I think you can see it. And that is going to break down into M aqueous, and I'm going to just make it +1 just for the sake of ease here, but it doesn't have to be, and X minus 1, and that is also aqueous. And I do apologize, but that's the way the textbook does it. They use X. Think of that as a capital X. Don't think of it as our little x that's in the equation, right? Everybody kind of see the difference there, so we don't get confused? Now, for all solubility product equations, right, we're going to do an ice table here. And notice, for whenever we talk about solubility, we're talking about the solid dissolving. And I could ask the question, and what does that mean? Do we include solids in the equilibrium expression law? Oh, look, I got to know. That's great. It's Monday morning. I was expecting. What? Anyway, but very good. You were on the ball. We don't even include that. So therefore, I put lines through that thing. It doesn't matter how much solid is there, as long as there's enough to form a saturated solution. That's all that matters in this situation. So we assume that there is enough to form a saturated solution. So we start with a bunch of solid in there. It doesn't matter how much. And before it's dissolved, we don't have any of that ions left. So again, we treat it as if we can control the equilibrium. Okay, we're going to put the solid in the water. Don't dissolve yet. Don't dissolve. Just wait. We're not ready to go. 0, 0. And then we say, go, dissolve. Dissolve as much as you can. And it happens. Because we have 1 and 1, what am I going to have here for change? X and X. And what's going to be the equilibrium concentration? X. Isn't this fun? Now, the reason I want to derive this is because when we're talking about a solid dissolving in pure water, and that's going to be important, because at the end of this little run, near the end of the week, on Thursday, when we do something called the common ion effect, we're going to do the same calculations, except it's not going to be in pure water. It's going to be in a solution that already contains some M or already contains some X. Now, that's a completely different situation. But if we're talking about a solid dissolving in pure water, so this right here represents, so the 0 means pure water, all right? And I don't need the quotes around that. I don't know why I put it on the second side. But the 0 represents that we've put it in pure water. Then if you're starting with an MX salt, this is always going to be true. You're always going to get X and X. There's no other way it can go. So now we can write it out. KSP equals, what's it going to be? X times X, right? It's always going to be X times X, which means KSP is always going to be equal to X squared, always for an MX. All right? So now all you need to do is identify what the salt is. All right. Now, what are we getting here? This number X actually represents the number of moles of this salt that has dissolved. Because we started with 0, and then when this stuff dissolved, X moles of it fell apart and became X and X. Does that make logical sense? So this X, which is this X, which is this X, is the number of moles of the salt that dissolved. That is what we call the molar solubility. All right. Now, that's what we want to find. In all of these questions, we might ask, what's the solubility of magnesium oxide? What's the molar solubility? And if the question is asking, what's the molar solubility, you're solving for X. X is the molar solubility. It is the amount of this stuff that dissolved to break apart into its ions. A question that you might get might be, if the molar solubility is, they give you a number, determine the KSP. There's your equation right there. If it's an MX salt, take the molar solubility and square it, and you have the KSP. It's that simple. If the question is, the KSP is, blah, 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 determine the molar solubility, what do I have to do with this equation to get the molar solubility all by itself? Yep. I need to take the square root, which means the root of KSP is equal to X, which is the molar solubility, and that will get you that. So today we're talking about molar solubility, the amount of substance that can dissolve in pure water, and that is the X. And if I have a salt that's made up of one metal atom and one negative ion, whether it be an atom like chloride or a polyatomic ion like chlorate, doesn't matter. As long as it's 1-to-1, that's going to get it for us. It's Monday. I'm moving slowly here at this point. I know it might seem quickly. Can I continue? Excellent. This is fun. Let's now talk about what if it's an MX2 or an M2X. Again, we could come up with some examples here. MX2. If you can think of one, you can tell me. So like a magnesium with a chloride, right? You do the crossover. So you'd have MgCl2, right? That would be an example of an MX2. What would be an M2X? I'd need a 1 and a 2, so I'd need like well, sodium oxide isn't good. Sodium's like soluble all the time. Maybe something like a rubidium sulfide or something like that. I have no idea. I don't know. It doesn't matter. But that would be an example, right? So if you had something like rubidium, Rb, and then a sulfur, and it would bring that over there, it would be an M2X, right? I should have maybe picked like silver. Silver would have been the one. Like rubidium, all those first ones are soluble. Like really, all those group 1 guys are soluble. I should have picked the silver or something. Silver sulfide would have been better. But anyway, it's okay. Quit being so critical. Jeepers. All right. MX2. I'm going to just use the MX2 as the example, but I'm hoping that you realize that whether I have MX2 or M2X, I'm always going to have one of the ions that is 1, all right? So we'll put this as a +2 just to make it work. And then the other ion, in this case, that is 2. In other words, it's going to fall apart to produce 2 of the one ion and 1 of the other ion. Essentially, there are 3 ions that enter the water in the dissolving of an MX2. Make sense? So now we're just going to go through the motions exactly the same way. Ice, solid, 0, 0. It's in pure water, right? We'll save the unpure water for later on. I guess impure water. And then X. And then what's this one going to be? 2X. Ooh. X, 2X. KSP equals. And here we got to be a little careful, but you guys are pretty good. The 2X is going to be 2X squared. So now I'm going to bring everything together. That's going to be equal to X times 4X. Oops, 4X squared. I dropped one Monday morning. Ooh, that's a good catch. Right, because I brought the squared in, 4X squared, which means this is going to be 4X cubed is going to be the KSP. And it's very logical. Because the 2x is going to be squared, the 4 comes from 2 squared, right? And the x cubed comes from the fact that there's 3 ions. If there's 3 ions, each one is going to possess an x, and it's going to make it a cubed. If you're asked to find the KSP, there it is. If you're asked to find the molar solubility, what's it going to be? You guys are bright. What's that going to rearrange and solve to, Christian? Yeah, very good. KSP divided by 4, because I bring the 4 down there, and it's a cubed root, and that is the molar solubility for an MX2. And that is always the case. Now, the drawback of memorizing derived equations is that you screw it up. You don't memorize it correctly. And then I can't give you the full marks. That's the pitfall of using the memorized equation. You could always derive it quickly. It's not hard to derive. If you think carefully about where all the numbers come from, you could logic it out quite quickly in your mind and figure out what the equation is. However you do that is up to you. But potentially for questions, I could ask, please derive the equation for determining the solubility of an MX2 in pure water, right? Or I could say, determine the molar solubility and just give the question. And if I don't ask for the derivation, you can just write down the equation. It's up to, it's up to you. But if you want to derive it, by all means, you can derive it, right? Okay, let's keep going here. We will do an MX3. And you know what? You might even now start to begin to think about what the MX3 is without even deriving it. If you just think carefully about where the 4 comes from and where the x cubed comes from, you might be able to come up with the equation yourself even without deriving it. Isn't that exciting? I'm not even going to put examples down for this. MX3 solid, M, and we'll call this plus 3 3x minus, again, it's aqueous, ice. So if I were to go way down here, KSP, 3 x's, 1 m. Do you think you can come up with the equation for the KSP? What's going to happen when you put all those numbers and those x's together? Can we do it without writing it down? Anybody up to some mental math here Monday morning? The gears are not even moving. Everybody's flying through the derivation. Good stuff. You don't want to think about it? What am I going to have in this position here for this guy? 3x. And what's going to happen to it in the equation? You got to cube it. So the 3x cubed, what's that going to become? 20. What's that? 27x cubed. I got another x kicking around. There you go, you got it. Didn't write down a darn thing. 27x to the 4th. Right? Because there's 4 ions. 4 ions. So it's got to be x to the 4th. That's where that comes from. And because that's a 3, I got to have to cube the 3, right? Okay, we'll go through step by step. KSP, what do we got? Nothing, 0, 0, x, 3x, x, 3x, x times 3x cubed. I'm jumping the gun. I'm going right to the bottom here. That's going to be 27x to the 4th. 27x to the 4th. There's your KSP. Hey, I wonder if my eraser works now that the color went back. Nope. I think that's an equipment error, not a software error. All right. And if you want the molar solubility, what's it going to be? Oh, just put her hand up about that high and then gave up on it. Then? Again, the 4th root comes from the fact that there's 4 ions, right? The 27 comes from the fact that the one with 3 ions is going to be cubed. So you can actually think about the numbers before you even do that. One last combination, an M2X3. Come on. You just think about it. Just think. It's going to become a 2M and a 3X. What are you going to do with those numbers? No? No one? No one wants to dive in? Well, what's the X part going to be on the end? X to the... How many ions are in there? Too much for Monday morning. Trying to help you memorize it, but oh well. Okay, M2X3 solid 2M. I'm not. This has got to be what, a +3, and this has got to be a 3X, and that's got to be like a -2 or something because it's got to cross over. It doesn't matter. 0, 0, 2X, 3X. What do we get? Yep. 108, x to the 5th, which is essentially 4 times 27, right? Because it's 2 squared times 3 cubed because of the 2 and 3. And therefore, the molar solubility is going to be the 5th root, because there's 5 ions, of the KSP over 108. All right. So, essentially now, the examples that I do, if I don't ask you to derive it, and by the way, I'm not going to ask you to derive it today. Here, we're just going to use the equations. All you've got to do is pick out the appropriate equation and use it. Now here I'm just defining molar solubility, all right? On a moles per liter basis, hence it's a molar solubility. It's the moles of solute required to create a saturated solution in 1 liter. Last year when we looked at solubility curves, we gave you a solubility in grams per 100 milliliters of water, all right? Now that could be converted to a molar solubility. All we would need is a molar mass. And we may even ask you for a mass solubility. Again, you would just use a conversion factor to convert it from a moles to a mass, right? So many grams per liter. But they are linked. So here's where these questions become difficult. We throw a question out to you that says, determine the molar solubility of barium sulfate, all right? Now, if I had you go through an ice table, you might have to ask the question, jeepers, which one is this? Is this given all the E's? Is this starting with I and going to E and all that type of stuff? But now we've reframed the question. We've reframed it, even though we've used all of our equilibrium abilities and our equilibrium, techniques to figure it out. If I'm asking you for molar solubility, what are you solving for? X. You're solving for X. It's the X in an ice table for something dissolving in pure water. Okay? What type of salt is this? Christian? It's an MX. 1 barium with 1 sulfate. Now, you don't even need to write out the formula for it if you didn't want to. If this is an MX, what's my equation for finding X? The square root of KSP. Now, when I started teaching grade 12, way back when it was OAC, I was of the view, make them do the ice table, make them do that thing, right? That question would have been out of 6. Write out the ice table, put in the X's, and add it up at the bottom. Way to go, check mark, check mark, check mark. Now that's out of 2. If I don't make you do the ice table, that's out of 2. Put the numbers in, get me an answer, all right? You don't have to write down barium, sulfate, solid, becoming Ba plus 2 plus SO4 minus 2. You don't have to, but if you want to do that to see that it's an MX, that's excellent as well. But I'm making that out of 2. The root of 1.1 times 10 to the minus 10. Again, power of 10 estimation. When you take the square root, what are you doing with the exponent on your power of 10? Monday morning pause. Extra time. Shauna does a stretch to psych me out. Excellent. Tyson? You divide it by 2, because, right, remember when you take the square root, it's like taking the half of the exponent. So you're looking at a minus 5 here somewhere. What do we got? What do you got, Jenna? 1.0 times 10 to the negative 5 times 10 to the negative 5. And because this is a molar solubility, I need units. Moles per liter. Oh, do I not give the K for that? Are you kidding me? I got to find silver chromate. Is that a chromate? Yes, it is. All right, I'm on it. 725. I hope it's there. I should just include it in the darn question. What? Well, there it is. 1.1 times 10 to the minus 12. 1.1 times 10 to the minus 12. KSP equals 1.1 times 10 to the minus 12. What kind of salt have we got here? What is this one? Shauna? M2X. 2 silvers and 1 chromate. Again, if you'd like, you could write it out, right? If you want to go Ag2CrO4 solid becoming, it's an equilibrium, 2Ag plus CrO4 minus 2. Now, you know what? In the act of doing that, if you haven't memorized the equation, you might start thinking, 2x and x, that's going to be squared, that's going to be 4x squared with another x. It all starts to come together in your mind, right? Or you've got it memorized, or you build the ice table. What is the equation? What's the equation? Oh, we have a... How's it going? Good. We have the equation for x for an MX2? Yep. Cubed root of the KSP over 4. Cubed root KSP over 4. 1.1 times 10 to the minus 12. Divided by 4. Cubed root. Now, if I'm taking a cubed root, what am I doing to the exponent on the power of 10 to do my estimation? A cubed root. It is to the power of 12. What did I say? Oh, sorry, 12. Correct. What am I doing to the exponent if I'm taking a cubed root for my estimation? Yep. Divide by 3, which means I'm in the what? 10 to the minus 4 there? All right. So what do we have here for a number? Somebody having close to 10 to the minus 4? Could be 10 to the minus 5, but close to it. Jess, what do you got? 6.5 times 10 to the negative 5. 6.5 times 10 to the negative 5. And again, that's moles per liter. I have no concerns if everything looks good. Yep. Here's an example of it. Notice the KSP is smaller in this question than it was in the previous one, right? There it was times 10 to the minus 10, but because it only had 2 ions and we took the square root, we've got 10 to the minus 5, right? Do we not get that number? Oh, now you're messing me up. What do we get? Oh, we do like it? Ooh, ooh. Oh, you look at. This is all under the root. So you divide by 4, then cube root. You divide by 4, then cube root. All right. Just for class president. She's voted in. Wasn't unanimous, but you won. Way to go. Again, I was trying to point out here that notice times 10 to the minus 12 might make you think it's significantly less soluble, but because we've got to take the cube root, 6.5 times 10 to the minus 5, in this case, 1.0 times 10 to the minus 5, they're really quite comparable in terms of their solubility, their molar solubility, all right? So that's why we say the KSP usually indicates that particular thing. Okay, determine the concentration of silver ions in a saturated solution of And ladies and gentlemen, this is a throwback to last year. This is just getting you thinking about how we can then determine the ions in solution. This is as simple as saying there are 2 silver ions in each silver chromate that dissolves. So we're going to take our previous answer and multiply it by 2, right? So we're simply, using that mole ratio to figure out how many silver ions. So it is that simple. What was the answer on the previous page? 6.5? Yeah. So something like this. Concentration of silver ions is going to be equal to 6.5 times 10 to the minus 5 moles per liter, and that was of the silver chromate. And if I'm going to do this like a conversion factor, and it doesn't even need to be done in this detail, but that's of Ag2CrO4, and then you just multiply it by the 2 silvers in each silver chromate. And again, that is super overkill. There's 2 silvers in it. Multiply it by 2, right? So I've just done that over the top at this level. Grade 11, I'm writing it out like that because I want you to see where all the steps come from. But if there's 2 silvers in it, then you're just doubling it, and what does that get me? That gets me, it's going to get me 1.3 times 10 to the minus 4. 1.3 times 10 to the minus 4 moles per liter of Ag plus, okay? So that's not anything to get stressed over. That's good old stoichiometry. Well, that's not stoichiometry. Conversion factor to convert into silver ions. And let's do some back the other way. Again, we're still just using the equations we've derived. It's actually a good lesson for Monday morning. It doesn't take a lot of thought. You just need to pick the right equation and away you go. Again, you don't have to write it out. You could just go with knowing that this is a particular type of salt and get the equation. But it doesn't hurt to write it out to see what type of salt it is. So what kind of salt is this? It's an MX. And whether you imagine that through, KSP is equal to What is it for an mx? Tyson? X squared. X squared. They give you the molar solubility. Put it in and square it. Ooh, ah. Something times 10 to the minus 10, but that's a 49, so I guess it's a minus 8. 4.9 something times 10 to the minus 8. I don't know. No, sorry, 9 times 10 to the minus 9. What is it? Tyson? 5.0 times 10 to the minus 9. And we don't put any units with it. It does have units. It would be moles squared per liter squared, but we're not going to worry about the units here. Okay? Okay with this? Like I said, pretty straightforward stuff. And again, one more. Just trying to give you all the combinations that you could encounter. I think we're almost there, and then I'll just let you work. What do we got? That's 2. Oh, I got one more after this, a 3. And then it's work. What do I have to do with this one? Yep. Yep. Into moles per liter. Yeah, and then put it into whatever the MX one is for that thing. You bet. So I've got to turn the 0.816 grams per 100 milliliters into moles per liter. I could do a good old C equals N over V, right? V is 0.1 liters. I just need to figure out how many moles of magnesium hydroxide is in 0.816 grams. How do I convert mass to moles? Oh, yeah, that's good. We haven't done that in a while. That's fun. It's fun. We need a molar mass. MgOH2. An OH has got to be what, 17? 17 times 2? I just put the O with the H. Magnesium, 24.3. I don't know what that is. Somebody tell me that number when you get it. 58.3 grams per mole. I like to do the C equals N over V, right? You know, that's the one that we've done, because now I'll convert that 0.816 times 58.3, and that's grams, 1 mole. And I am running out of space here. Terrible. And then that's going to be over 0.100 liters. I'll take the N when you get it, and then I'll take the C when you get it. Oh, I want 2 significant digits, you think? I think I want another significant digit on the end of that. Oh, 40. It's 340. It's still 340, right? 0. Was that a 0? 0, 1, 3, 40, 140 moles. 0.0140 moles. And then we move that decimal over once. So what's that? 0.140 moles per liter. Did I do that right so far? And this is what kind of a salt? Oh, what did I do? We're good? And what kind of salt is that? MX2. So KSP 4x cubed. And if you didn't clear your calculator, you still have that number in it. 4 times 0.140 cubed. What do you got, Kristen? You didn't finish it? You had all the answers and then you stopped right there? That's too bad. Monday morning. Yes, what do you got? Times 10 to the negative 2. All right. And could probably have had another significant digit on there, but hey, it's Monday. I don't care that much. What's that? Oh, 1.10. Thank you. Okay. So there's just converting from mass to moles. One last one here. That's fun. So this kind of brings everything around again to comparing those KSPs. Right? I said at the beginning it usually means, you know, the smaller the KSP, the less soluble it is. But this one straight up compares two KSPs. So the KSP of an MX salt is 4.5 times 10 to the minus 8. What would the KSP be of an MX2 salt that has the same molar solubility? What would you like to do with this? Or what can we do to begin with? Yeah, Tyson, what do you got? Yep, solve for the solubility. Yep, go ahead. What else would you do? Yeah, find the X, the molar solubility of that MX data, and then take that solubility and put it into the MX2 equation and find the KSP. Then we can compare those directly. That would mean that they would have the same molar solubility. So X is equal to, for an MX, I think it's what? It's just root KSP, isn't it? Do a quick estimation in your mind, the root of 10 to the negative 8, so that you know you're on the right track. Two significant digits. 3.3 times 10 to the minus 4. 10 to the minus 44. 10 to the minus 44. You didn't do your estimation, did you? What do we have for a number? Yep, Tyson. 2.12 times 10 to the minus 4. Not bad to keep an extra digit because we'll round back at the end. And therefore, KSP for an MX2, what's that going to be? What is it? 4x cubed? 4x cubed for 2.12 times 10 to the minus 4 cubed. What do you got? 3.82. We could probably round it back, but again, we're just comparing. It's not a big deal. Times 10 to the negative, sorry, I missed that. 11. And so as you can see, same solubility, MX just has a 10 to the minus 8, but an MX2 has 10 to the minus 11, right? So you can't just compare the Ks straight up, right, to determine whether one is more soluble or not. You also have to look at what type of salt it is. There you go. And I was going to do this example again just to compare it, but no, we don't want to do that. So there's some homework. So again, for homework, there are a handful of textbook questions, but you also can do all of Part A on this solubility product sheet. I'm very sure that in the solutions, you'll find the written solutions for this. And you'll notice in that it says number 1 is text questions, and that is old text questions. I haven't had a chance to edit this page. So where it says text questions, page 486, 1 to 4, and all that stuff, you can discard that or just ignore that. And that's going to be true all the way down this page. The text questions are always that first thing on there, and I haven't updated this page for the new textbook, right? So textbook questions are right there on the PowerPoint, and then you can do these as well.